In this video, we will be doing some examples from section 12.1. We're going to be sketching these vector valued functions and coming up with a piecewise vector valued function for a path. You can go ahead and try these on your own, pause the video, and come back and see my solutions. For the first one, we have the vector valued function r of t equals t squared plus ti plus t squared minus tj. There are a few ways of approaching sketching these vector valued functions, and one way is to make a table of values. Suppose we start off with a table. Our independent variable is t. So when you plug in different values of t, you get different output values for your vector valued function. So we have r of t. So let's start off with just a few values for t. T equals -2, t equals -1, 0, 1, and 2. You can plug those in for t in the vector valued function, and the results are vectors. So when you plug in t equals -2 into the vector valued function, the resulting vector is the vector 2i plus 6j. And if you plug in -1, the resulting vector is 0i plus 2j. Plug in t equals 0 and you get the 0 vector. Plug in 1 and you get the vector 2i plus 0j. And when you plug in 2, you get the vector 6i plus 2j. Now the vector valued function is the path that's created by the endpoints of those vectors drawn from the origin. You can make a quick sketch here. And when you, at t equals -2, the vector has components 2i plus 6j. So the endpoint of that vector is the point 2, 6. That's a point on the path when t equals -2. When t equals -1, the vector is 2j. So from the origin, you would go to that point that's 2 units up. Okay, so again, the vector would be that little vector from here, the endpoints of those vectors from the origin. When t equals 0, you have the 0 vector. When t equals 1, you have the 2i vector. And when t equals 2, you have 6i. 1, 2, 3, 4, 5, 6, and 2j. The endpoint of that vector would be here. So it appears that the path is moving in this direction from this point and going in that direction. We can assume that it's going to be making this shape right here. So we have the vector valued function represents the path in space defined by those endpoints of the vector. So that's one way of looking at it. Another way of looking at it is by using technology. So if we use a graphing calculator, make sure your mode is in parametric mode. You're going to go to the y equals, and you're going to replace the x with t squared plus 2t. And then you're going to replace the y with t squared minus t. Let's do that again. So once you enter what x and y is equal to from the vector valued function, I want to go back to the mode, and I typically use radian mode and parametric when I'm sketching these vector valued functions. And then when I want to do the graph, I'm going to press the zoom button and start off with a standard zoom, zoom 6. When you start off with a standard zoom, you don't get a complete graph, and the reason why can be found by pressing the window button on the top of your calculator, and the default when you do a standard zoom in radian mode, the default is a Tmin of 0 and a Tmax of 6.2. That's 2 pi with a T-step and the Xmin and Xmax is shown. To get a more complete graph, you want to adjust the time, min, and max so that you can see more of the graph. In fact, I can change the Tmin to -5, so it'll graph all the Tmins from t equals -5 all the way up to 6.28. I'm not going to make any other changes and then press the graph button. So now you see that complete graph, and notice the orientation. The way that it was sketched was from the top around the origin and off to the right side of the screen. So when you're sketching by hand, you do want to make sure you put that arrow to denote the orientation of the path. All right, let's look at the next example. Let's use a graphing calculator to sketch the path that's defined by 2 cosine cubed ti plus 2 sine cubed tj. To sketch this path with a graphing calculator, I'm going to, again, make sure your mode is in parametric mode. I'm using radians. Go to the y equals and let's write this as 2. Now to do the cubed part, I'm going to use parentheses and then enter cosine of t, close the parentheses twice, and then you can raise it to the third power, or you can get that third power by pressing the math and choosing number 3. So this is how it's going to look like when you sketch, when you enter in your calculator 2 cosine t, that entire quantity of cosine t is cubed. Now do the same thing for the y. That's your 2. I'm going to use parentheses, sine t, close the parentheses twice, and then cube the sine t. Now I'm going to do my standard zoom, zoom 6, to see the sketch of the vector valued function. Not really that easy to see, so let's go ahead and zoom in. I'm going to press zoom number 2 and enter, and you see a more complete graph. This is referred to as a hypocycloid or hypercycloid. I'm going to make a few adjustments to get a nicer looking graph, and I can do that by pressing the window button. And the window default when you do the standard zoom in radian mode is from 0 to 2 pi with a t-step of 0.13. I'm going to make that t-step a little bit smaller, and that's going to increase the accuracy of the graph. So I'm going to change it to 0.05. And then another thing I'm going to do is go to the y equals, use the arrow over to the left of the x equals, and you see a line. That's your default line. I'm going to change that to a line with a ball so you can clearly see the orientation of the path. I'm going to press enter, and I see the next thing that shows up is that thick line. It would graph a thick line. Press enter again. I get this little line with a O that's going to look like a ball going through and tracing out the path. So I'm going to make that change and press graph so you can see where it begins. It's going to move up. It's going a little bit slower now, and that happens when you decrease the t-step size. The smaller the t-step, the more accurate the graph, but also the smaller the t-step, the slower the graph goes. So you see that shape. Now when you press trace, you can see at t equals 0, the location of the path on the path is the point 20. And if you move your arrow to the right, you can see as time increases, the orientation of the path is displayed here going counterclockwise. So if you wanted to sketch the graph by hand, you can make a table of values. You can find that table of values by plugging in values for t. At t equals 0, you're at the point 20. You can change different values of time. You can say t equals, say, pi over 2. You see you're at this point up here at 0, 2, t equals pi. You're at the point -2, 0, and at t equals 3 pi over 2. You're at the point down here at 0, -2, and when t equals 2 pi, you see you come back to where we started. Okay, and the reason why this is not showing up as invalid dimension is that when you set up the window, it doesn't exactly get to 2 pi. You would need to make an adjustment there. So when you make a table using different values for t, I'm using t equals 0, pi over 2, pi, 3 pi over 2, and so on. You can evaluate the vector valued function at those specific values of time, and you can find the corresponding vectors that will indicate the location of the path on the path. So t equals 0, we get the point cosine of 0 is 1, so you get a vector with components. I'm going to switch to the angle bracket notation here. The the vector would be the vector 2, 0 at t equals pi over 2. You get the vector 0, 2. At t equals pi, you get the vector -2, 0. At t equals 3 pi over 2, you get the vector 0, -2. And at t equals 2 pi, you get the vector 2, 0. So with those, you can sketch and indicate the orientation of the path.